Hello. We're going to look now at the properties and applications of the cross product. So a lot of these properties we dug up in the derivations video. So I'm going to summarize those and then talk through some of the others just to get a sense for what the cross product represents and means, how we work with it. And then we'll go through some applications and examples with torque. So first, the cross product creates a vector which is perpendicular to both u and v, the ones used in forming it, and that vector follows the right-hand rule in its construction to figure out which direction it's pointing. The magnitude of that cross product is the magnitude of u times magnitude of v times the sine of the angle, which is maximized, obviously, when the angle is 9 degrees, or when u and v are perpendicular. This magnitude of the vector is the area of the parallelogram formed by u and v. Essentially, it's the area of the parallelogram at the base of the cross product. So the cross product is formed from this parallelogram as a foundation up. And there's a correspondence between the area of that parallelogram and the length of the cross product vector. It's kind of interesting. Note that sometimes we're interested in the area of triangles, and triangles are essentially just half of parallelograms. So we can take half of the cross product's magnitude to find the area of those triangles. The cross product is 0 if u and v are parallel, which means one is a multiple of the other. And then finally, the cross product requires two vectors. This isn't really new. I mean, it's a way of multiplying two vectors together, but we have to be careful to make sure that what we have around the cross product are vectors. For example, c times u is a scalar multiple of vector. That's a vector. Or throw on some vector notation just to make sure we can distinguish them from each other. Lost it there. So c times u is a vector, so we have a vector on this side. And then on the other side, we have v cross w. Well, v cross w is a vector. So we have a vector on both sides, so that's a valid operation. Whereas over here, v dotted with w is a scalar. And so we have a scalar on one side and a vector on the other. We can't cross a scalar with a vector. Okay. So that's just an idea to keep in mind on what we can and can't do with the cross product, similar to the dot product. Okay, so now let's look at the application to torque. Okay, so now let's look at the application to torque and some examples with the cross product. First, torque is a force, but it's a force related to rotation. It's the twisting effect resulting from a force F applied or acting at a distance r, described as a moment arm or radial distance, from the axis of rotation with angle theta. Okay, that's a lot. Let's draw a picture to visualize what's going on. Let's say we have a bolt and a wrench over that bolt. The wrench provides the distance from the axis of rotation. We're going to apply a force to that wrench to either tighten or loosen that bolt. So right now the force is being applied at the handle or near enough, and the radius or moment arm is the point on that wrench where we're applying the force. The angle theta is the angle between R and F. Get their hats back on there, or not hats, their vector notation. And it's easiest to see what the angle looks like if we move F, copy it over so that R and F start at the same place, basically drawing them from the same origin. Now, the result of these two provides the torque through the cross product. And that cross product is R crossed with F, giving us the torque. Now, in this case, it's going upwards because F is being applied on this side. However, if we think about the direction the wrench is being twisted, this wrench is being twisted around counterclockwise. You can think of that as lefty-loosey. We are loosening this bolt by drawing it in this way. If I had drawn the force pointing the other direction, we would be tightening, going clockwise, righty-tighty. Righty-tighty, lefty-loosey, right? Those quick those quick ways of remembering how to tighten and loosen bolts are just the results of applying the cross product to a force that's moving the moment arm counterclockwise or clockwise. Okay, cool. So I'll label that torque. No, not with the G. I'll try that again. Ah, grief. Okay. For some reason, I really want to put a G in that torque. There we go. Torque equals. I noticed in the book they use a tau, so we could represent that with a tau if we want to. I want to compute the torque and its magnitude for force. Let's say we're looking at yeah. 2I hat minus 10J hat plus 8K hat at distance r five I hat plus j hat minus 6 k hat. Okay, to compute this cross product, I first want to put them in shorthand notation, get them lined up, and then I want to also make sure I have the right order. So torque is R cross F, not F cross R. So I'm going to write R above. Now I can use the basis form very similar to how I used the shorthand form, but you kind of have a lot of ij and k's that get into the way. So I'm going to write it in that shorthand form again. 5, 1, negative 6, 2, negative 10, and 8. And then throw a little ijk up on top to compute R cross F. I hat, take the determinant left over. We have an 8. And then minus 60. Then j hat. Yeah, I need some room, so I'm going to write that down a little lower. Minus 60. J hat is a minus, cancel out, or cover up that second column. 5 times 8, 40, minus a negative 12, so plus 12. And then K hat, cover up that third column. Negative 50 minus 2. Okay. So, simplify this down. We get 8 minus 60. That's 60 minus 8 negated. Negative 52. Here we have a negative of 40 plus 12. That's also a negative 52. And that one is a negative 52 as well. Okay, so interesting. My torque is ascribed by the same value in each thing, so I can factor that out if I need to, and I need to right now. I'm going to find the magnitude of the torque. How large is the forcing, the rotational force created? I first want to factor out the negative 52 and then take the magnitude of the resulting 1, 1, 1. So I have a positive 52 times the square root of 3. Now, quick check. Force is in newtons. Radial arm is in distance, like meters. So this twisting effect from the force is actually energy. Newton meters, or joules. The standard units for force is newtons. Standard unit for distance is in meters, scientifically speaking. And so we often will see the, want to think about what it results. Well, we will see the resulting energy either described in terms of Newton meters or joules if you want to. So just one way to kind of think about the units. And that is a good reminder because the cross product feels a little bit surreal when we're thinking about units. Like, what do you mean units? Well, it's just a product, right? We're just multiplying these quantities together in a different way. And so we multiply their units accordingly. Okay, so what else do we want to glean from this piece? We have the moment arm, we have the force, we computed the torque. The torque itself was interesting, but we gravitated towards the magnitude because that tells us how large of a twisting energy we're getting from applying force. But I'm interested on how effective was my twisting. How effective was the force applied? And that question is really about the angle. What is the angle? Or I don't really care what the angle is. Is it close to 90 degrees or is it closer to 0? Now to check to see where the angle is, I could compute the angle directly, but a very quick check is taking the dot product. The dot product will tell me the cosine of the angle. So if I dot these two together, I get a 10 minus 10 minus 48. Now what does that mean? This means, first, it's not 0. If it were 0, then we would be optimal. We would be applying the force optimally. So I didn't compute the angle. I didn't go through the steps of seeing exactly how effective it was, but I do know from a very quick check that is not an optimal application of my force. Oh, interesting. So the dot product can be useful in checking or evaluating our cross product. We can, of course, compute the angle from the magnitude calculation over here by dividing by the two pieces. I'll do that over here. Angle theta is equal to the magnitude of r cross f divided, I should say the sine. Sine of the angle is equal to the magnitude of r cross f divided magnitude of r, magnitude of f. And so I can find theta by the sine inverse of my 52 root 3 divided by the two magnitudes specifically. This is quite a bit more work, but it can be done. So let's take a quick look at it. The first length would be 25 plus 1, 26 plus 36, so that would be 62. The second one would be 4 plus 100 plus 64, so 68, 168. And we have to be a little bit careful on this to make sure that, no, it's positive, I think. Good. So take the sine inverse of that to find our angle between negative pi over 2 and between negative 90 degrees and 90 degrees. So a lot more work to actually find the angle, very quick to know whether the angle is 90 degrees or not. Okay, let's do it. Just a couple more examples with the cross product just to see how it works, get a feel for it, a cool down, if you will. Okay, so we're going to cool down with 3 examples, just seeing what the cross product is and its magnitude, and maybe checking the dot product along the way to see how effectively these vectors are crossing together. Again, I've written all of them in the format so they can be easily visualized as being in the 3x3 matrix by throwing on I, J, K. So we'll first compute cross product. I hat cover up the first column. We get a positive 18 minus 10. Then for the j hat component, I first write a negative to remember that alternating sign, and then cover up the second column. And then finally cover up the third column. Get that result. Simplify it down. And if it's helpful, let me factor out 2. That's helpful because when we compute the magnitude, we get that 2 out, absolute value of it, times the square root of the inner pieces. So that's square root of 16 plus 49 plus 36. Okay, so 6, 12, 21. 60.1. So there's our first magnitude. Again, going through the process of computing the cross product, simplifying down, don't forget the negative on the alternating sign, factoring out a common term, and then computing the magnitudes through that common term, and then the sum of the squares on the inside of the square root. Okay, next one up. And you can pause the video and work on these by yourself, but take a minute. Now I'll go on. Well, that one's surprising. Notice how we get cancellations on each term, which means our vector is 0 and its magnitude is 0. That's only possible if these two vectors are multiples of each other, if they're parallel. We check. -2, -2, -2. Yes, they are. So if we recognize that two vectors are parallel at the get-go, we know that the result should be 0. So keep that in mind. And the last one. And nothing to factor out there. Okay. Whew. Wish you luck on the rest of your practice with cross products as well as dot products as we wrap up algebra with vectors.